For this screencast, I'm going to be doing problem number 18 from 13.3. It asks us to find it asks us to find multiple things. The first of which is the projection of the vector f we see here onto the vector v. The first thing we need to do is turn vector v into a unit vector, which is, we'll use it later down the road, but I like to do it first because it's the easiest bit. We find the unit vector by dividing the original vector, which is in this case 3i plus 4j, by the magnitude of the vector itself, which can be calculated using the Pythagorean theorem. You can see here the progression. It's a relatively simple mathematical thing, Bob. From here we're going to move on and actually find the dot product of, we're going to put that away for now, and we're going to find the dot product between v and f, which will give us a scalar, and this scalar will be the magnitude of f parallel here. So here we go. Because in this case the dot product is only dealing in 2 dimensions, it makes it a little bit easier, and you end up with 12i plus, or wait, no, there's no I there because this has no direction. So I end up with 12 plus 4, which gives us 16 as a scalar. From here we can take the scalar 16, which is, it's just a number, and multiply it by the unit vector, which we calculated before. So from here it's a simple multiplication and distribution. So then we end up with, so from here on out you can see I gave you the fractions and then the decimal approximations if you're so inclined, but either one is equivalent to f parallel. Yay! But here we go. That's only part A, so moving on to part B, which asks us to find f perpendicular. Because we already found f parallel, finding f perpendicular is going to be relatively easy. We can use the kind of definition that f, in this case, is equivalent to f parallel plus f perpendicular. But because we are looking for f perpendicular, it's simple algebra reorganization, and we get f parallel is equivalent to, f perpendicular, misspoke. F perpendicular is equivalent to f minus f parallel. All done now. You can see it's just simple subtraction from subtraction of vectors, and from there we get negative 5.6i minus 11.8j is f perpendicular. But wait, there's more. Now that we finished part B, we move on to part C, which asks us to find the amount of work done through the displacement v. So essentially it's asking how much work is done by the force in the direction of v. Using a kind of simplified version of the diagram I had above, you can see that here's vector v, and we want to find out how much work that the force F is actually doing in the direction of v. So that's why we found everything we did. So what you want to do for this is you're going to want to multiply F parallel, which is the amount of force along the displacement, by the magnitude of the displacement, which is scalar, which will give you work. Actually, correction. It's going to be the magnitudes multiplied together, because since we found F parallel, the force acts in that distance. First of all, we need to find the magnitude of F parallel. F parallel, if you recall, is 9.6 I plus 12.8j. So essentially, using the Pythagorean theorem, we square both of the magnitudes of the I and the j, and take the square root of that, of their sum, which conveniently they add up to this 256, and that happens to be a perfect square, which is 16, which is really nice. So it's going to end up being 16 times magnitude of v equals work. And we figured out that the magnitude of v was actually 5 earlier, so that's going to end up equaling 80 joules, if you want to be specific. And that is all. Thank you again for watching.